So welcome to the second lecture involving entropy and thermodynamics to give us a Gibbs free energy and why some things work and some things don't. So we need to be reminded of three laws of thermodynamics. The first law, the delta E of the universe is zero. Energy can't be created or destroyed. The second law, the entropy change of the universe is greater than or equal to zero. If nothing is happening, the change is zero. If something is happening, the entropy has to be increasing. And the third law, which creates the scale for entropy, a perfect crystal at 0 Kelvin has zero entropy. Making use of the second law of thermodynamics, the entropy change of the universe is the entropy change of the system plus the entropy change of the surroundings. Since the surroundings has much more stuff in it usually, any amount of energy transferred to the surroundings is going to provide the greatest amount of choices about what it does with it. And so delta H divided by T replaces the delta S of the surroundings. But we do have to make a small correction. Since delta H is for the system, the result in the surroundings is minus delta H. And that gets us a nice simple equation. Well, we can simplify it a little bit. We can simply multiply through by minus T. And so on the left, we get minus T times the entropy change of the universe equals delta H minus T delta S, where in this case, both delta H and delta S refer to the system. And we talk about the Gibbs free energy. We can form a nice simple table for Gibbs free energy based on the signs of delta H and delta S. If delta H is minus, that it's an exothermic process and the entropy change increases, then delta G is always going to have a negative value. And that's okay with the universe. On the other hand, when you have an endothermic process where there's a reduction in entropy, delta G is always going to be positive, and that's not good. The minus sign is always negative. T is, of course, absolute temperature, and the only way that can have a positive value is if the entropy change of the universe is negative, and the second law of thermodynamics says that's not happening. And so a reaction with those processes will never happen. If the sign of delta H and delta S are the same, we have a choice. It's either neither always positive or always negative. It depends. It depends on what? Well, it depends on which term is larger, delta H or delta S. Delta H doesn't vary much under most conditions, but delta S depends directly on temperature. The higher the temperature is, the more the entropy term becomes important. At low temperature, the delta H will dominate. And for an endothermic reaction, that means delta G will be positive. At higher temperatures, at some point, the delta S term will take over, and the reaction will become negative, and therefore favorable to happen. If both signs are negative, you have sort of the opposite effect. When the delta H is dominant, at low temperatures, the reaction is favorable, but raising the temperature makes it unfavorable as the entropy term takes over. A simple example of an endothermic process that includes an increase in entropy, of course, is melting a solid to a liquid. It takes energy to break up the lattice of the solid, whereas the liquid, of course, is going to have more entropy than the liquid will have more entropy than the solid does. Looking at it the other way around, changing the liquid into the solid is going to obviously be a reduction in entropy. But to make the solid freeze into the solid, you have to take the energy out. You have to make it an exothermic process. Consider a reaction like reacting ammonia gas with hydrogen chloride gas to give you ammonium chloride solid. Should this reaction be favorable at 25 degrees and 1 atmosphere pressure? And the answer, of course, is maybe. You'd expect the delta H of this reaction to be exothermic. Changing small things into large things always involves bonding, and bonding is, of course, always an exothermic process. Meanwhile, changing the gases to the solid rather, is going to be a huge drop in entropy, because the choices the solid has for location are much less than the gas. The book talks about positional probability here. So the signs are both going to be negative. So it'll be temperature dependent. So you have to go to the appendix in the back of the book and look up the heats of formation for ammonia, HCl, and ammonium chloride. And we find out that the total is minus 176. You also have to look up the entropies for those three materials. And in this case, it ends up at 284. And so the delta G of the reaction is minus 91.4 kilojoules. 91.4 kilojoules? Yeah, 91.4 kilojoules. Because, of course, the heat of formation is, in fact, 176 kilojoules per mole. But the entropy term is in joules per mole. You're multiplying by 298 Kelvin times 28.4 joules per Kelvin. And the difference is going to be 91.4 kilojoules. This is thermodynamics. And the four things you have to spend all your time worrying about in thermodynamics are signs and units, amounts and states. But nonetheless, that means the reaction is in fact really favorable at room temperature and 1 atmosphere pressure. But suppose we're talking about 400 degrees Celsius. What is that going to do for the reaction? Well, the delta H is still going to be minus 176 kilojoules, but now you're multiplying the minus 284 joules per Kelvin by 673 Kelvin. The result is plus 15.1 kilojoules. So at 400 degrees, this reaction is unfavorable, which means it would actually prefer to run in the opposite direction. Any reaction with a positive delta G actually wants to run the other way. So, we'll consider a reaction. Reacting sulfuric acid with sodium hydroxide in aqueous solution to form sodium sulfate and water. What's the delta H0 for this reaction? What's the delta S0 for this reaction? And finally, of course, what would the delta G0 be for this reaction? And that's where we'll pick it up in the next tape. Go ahead and solve for delta H0, delta S0, and delta G0 for this reaction using the appendix in the back of the book before going on to the next video.